All right, this is lesson 8.4, and we want to look at L'Hopital's rule. Now, L'Hopital came up with this rule to try to figure out how to evaluate limits, and it works as long as we have a couple different situations. One is an indeterminate form of 0 over 0 or infinity over infinity. Any one could be positive or negative. And this is known as L'Hopital's rule. So if we have a limit that is indeterminate, and we worked with many of these early on, 0 over 0 or infinity over infinity, then this limit of the two functions is going to be equivalent to their limit of their derivatives, respective derivatives for f and for g. You're not going to be necessarily using a quotient rule here, but you're just going to take the derivative of the top, derivative of the bottom, and see what happens. So let's try an example here. Now before we do this, we're kind of jumping the gun a little bit, but it makes more sense if we know what this is. This you'll find out later, derivative of e to the x is e to the x. That's kind of a funky one. So you have to know that for this particular unit. It's not a huge deal, so let's go through an example and see how this works. So if I take infinity and plug it in here, that's going to be infinity. This one's going to be infinity. Now you might ask which one's growing to infinity faster. I hope you understand that the denominator would grow faster. But we can use L'Hopital's rule to help us out with that too, to make it so that it isn't infinity to infinity. So we go x goes to infinity of, well, what's the derivative of the numerator? What's the derivative of x? Well, it's a 1. What's the derivative of the denominator? Well, we told you that derivative of e to the x is e to the x. Now we have a definitive answer for this. This one is going to go to 0 because the denominator grows faster than this 1 in the numerator, and so we do end up with 0. So if we want to compare polynomials and exponentials, great way to do that. How about number 2? Very similar situation, infinity over infinity. Well, if I have this, and remember it has to be this case in order to use L'Hopital's. Has to be the case to use L'Hopital's rule. So the limit as x goes to infinity of the derivative of the numerator is e to the x. Derivative of the denominator would be 1. This goes off to infinity, so we really can't evaluate it per se, but it does go off to infinity. Number 3, you can try these too and jump ahead of me. Is this one of the indeterminate forms? I see 0, I see, oh, it's a 1. Oh, we can't use it then. But what is 0 over 1? It's just 0. So we didn't need to use L'Hopital's rule, nor could we use it, because it doesn't satisfy one of these conditions. How about this one here? Well, this one is going to be a 1 over, well, what does this go to? Well, it goes to 0, but what kind of 0? Well, it's going to be a negative value. So then this one will end up going to a number over a very, very small number. Well, when that happens, we go off to infinity. But since this is a negative, this is going to be negative infinity. We did say that maybe we could say that this does not exist, but graphically we like to know what that goes to, and so that's going to be negative infinity. Now for number 5, I had the wrong one listed there, but I have this one on your notes, and so the limit as x approaches negative 1 of 2x squared and all this stuff. Well, if I factor this one, 2x squared minus 1, I like that a little bit better. And as x goes to negative 1 and I plug it in, I'm going to get 0 over 0. So I can use L'Hopital's rule for this. So except for on your page it says without L'Hopital's rule, so I'm going to factor and cancel. So the limit as x approaches negative 1 of 2x minus 1, x plus 1, and notice my x plus 1's cancel. And so if I plug in negative 1, I'm going to get 2 times negative 2, which would be negative 4. So let's try it now with L'Hopital's rule. So if I have this for number 6, limit as x approaches negative 1, take the derivative of the top. Well, that's going to be 4x. Take the derivative of the bottom, it's going to be 1. If I plug in negative 1, I'm going to get negative 4. Both ways work, and they are equivalent. Number 7 that you have there, we can use L'Hopital's rule because if I plug in 0, it's going to be, no, it's not going to be 0 over 0, is it? What is it going to be? It's going to be 0 over 1. So this one would be 0 again. Very similar to that previous one we do. When we add this one in, what if I do the limit as x goes to infinity, though, of 3x squared all over e to the x? Now with this one, I get infinity over infinity. I hope you can see that. So if I rewrite this, the limit as x approaches infinity, I'm going to take the derivative of the top. The derivative of the top is going to be 6x. The derivative of the bottom we said was e to the x. I still have infinity over infinity, but let's go one more time. Limit as x approaches infinity of 6 all over e to the x. Now what do we get? Well, this will go to 0 because, and if we graph this, sure enough, we do end up going to 0 here, and then as we go to infinity, we also go to 0. That's what it looks like, and so our analysis was correct. So we do not want to use L'Hopital's rule just because a problem looks like a candidate for the rule. Examples 3 and 4 are not candidates for L'Hopital because direct substitution does not yield 0 over 0 or infinity over infinity. I think that's the right numbers, 3 and 4, maybe not. But this one right here does not yield that result, so we can't use L'Hopital's. This one does because it's infinity over infinity. If using L'Hopital's rule leaves you in the form, one of those, then you can use the rule again. It is a process by which can be repeated many times. Just remember to use direct substitution each step to make sure that it can be used. You have to do this every time. So how about if we evaluate x going to negative infinity of x squared over e to the negative x. So if we plug in negative infinity, well, this bottom will be e to the positive big number. So this is going to go off to infinity. This is going to go off to infinity. So yes, we can use it. So if I have this, the limit as x approaches negative infinity, I'm going to get 2x all over e to the negative x. Now you don't know this, but you got to chain off that negative. And so this thing still gives me problems because I'm going to be negative infinity over negative infinity. So let's try one more time. So if it doesn't resolve your problem, keep on going. So now the numerator derivative is going to be 2, and the denominator derivative is going to go back to e to the negative x. So if I do plug these in now, the 2 on top is a constant, and then if I plug in negative infinity into here, this is going to be e to the infinity, which is a very, very big number. So overall, we're going to end up with 0. So that resolved the problem for me by doing multiple steps on L'Hopital's rule. Now finally, I have this on your paper to compare these different functions. What if we wanted to put these all in order from growing the fastest to not growing the fastest? In other words, I want to do it the other way. Y equal to 1 is not growing very fast at all. In fact, it's not growing at all. And then if I move on to these different ones, a linear is going to be growing faster in the next order. What's going to be after that? Well, y equals x squared. How do we compare polynomials and exponentials? And I did make a mistake in here. I think that the log function, remember the log function looks like this, and it grows very slowly. So this one would be ln x slipped in there. So I've used this, 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 and this. Now, if I do the next one of these three, which one's going to be growing faster, a polynomial here or exponential? Well, I think it's a polynomial. So y is equal to x to the 10th. And then the exponential will go after that. So that's kind of a rank order of growing fast for big X. What about this one, factorial? Well, for e to the x, that means you're going to be multiplying repetitively by e. For this one, x factorial, you're going to be multiplying repetitively by a bigger and bigger and bigger and bigger number than e. And so this one is the one that actually grows the most. We don't know the derivative of this, so we won't worry about that, but that's kind of a nice thing to know. So what does this mean for us? This means that if I see the limit as x approaches infinity, and I'm talking about going to infinity, of, for instance, x squared all over e to the x. Well, we did L'Hopital's, But with this rank order, it also kind of tells me that the exponential grows faster than the x squared. So the bottom's going to grow faster than the top. So this is going to go off to infinity. Now you can use L'Hopital's, and you should, to verify it, but it is something that should be intuitive to you as well when you're thinking about these functions. All right, that's it for L'Hopital's. I hope you enjoyed this. Thanks for listening. Have a great day.